Welcome back. Today we're going to look at nodal analysis, and these circuits involve voltage sources. If you go back and look at watch the previous lecture on nodal analysis, you'll notice that none of the circuits we looked at had voltage sources. They had nothing but resistors and current sources. And so we'll see in this lecture that the voltage sources do give us a little bit of heartburn, and we have to introduce the idea of supernodes. As a review, nodal analysis. Remember, nodal analysis is a systematic application of KCL to solve circuits. We have a recipe, 5 steps. If we have n nodes in our circuit, then we are going to expect n-1 equations, KCL equations, in terms of n-1 unknowns, which are the n-1 node voltages. Alright, so if we're going to see nodal analysis that has voltage sources involved, let's just jump in and do an example. So here we have a circuit where we have a voltage source, and this is very similar to one we looked at in the previous lecture, but now we have the 7-volt voltage source. So let's do nodal analysis. Nodal analysis, we begin with finding how many nodes are in the circuit, and you can color these, but you'll see that we have 3 nodes. N equals 3. We have the top left node, the top right node, and then we also have the bottom node. Step 2, define a reference node. And so for a reference node, well, I'll just pick the one at the bottom. It's at the bottom, and it doesn't, it seems to be a little bit more complicated. So, step 3, define the n-1 node voltages with respect to the reference node. So we can define a voltage here, plus to minus. All right, but again, we don't normally write it that way because it gets kind of cluttered. So how we normally write it is, we'll say that this is voltage V1. And then we have a voltage which is going to be plus to minus with respect to the reference, and we'll call this V2. All right. Next step, write the n-1, in this case 2, KCL equations. So write KCL at each node. And so I like to write the currents leaving each node because it sets up the passive sign convention naturally for us. So what is the, we're going to write KCL at node 1, and we're interested in the current going in this direction. And the current going in this direction, the arrow is opposite of what's drawn on the circuit, so we know that the current going down is going to be a minus 3 amperes. And then we're looking for the current going down in this direction. And remember, when we have V1, that's really plus to minus V1, so the current is already directed into the positive terminal, the passive sign convention. So the current going down is going to be plus, and the value of that current is going to be, we got a voltage V1 going through a 2 ohm resistor, so the current going down is V1 over 2. And now we need the current going in this direction, and so the current going to the right is going to be, well, this is a voltage source. Remember the definition of a voltage source. A voltage source, in this case, maintains 7 volts, plus on the left, minus on the right, 7 volts across it, no matter what the current is flowing through it. So remember, go back to the discussion on voltage sources. A voltage source maintains a voltage, and the current can be anything it wants. The current flowing through a voltage source is going to be whatever makes the rest of the circuit happy. There is no relationship between the 7 volts and the current. The current can be literally anything. So at this point, we don't know what this current is. So what do? Well, let's just give it a name and keep on going. So we'll call it I question mark. So we get I question mark, and that's all of them, equals 0. Okay, so let's hop over and do KCL for equation 2, for node 2. What's the current going down in this direction? Well, the currents line up, so it's going to be minus 2 amperes. What's the current flowing down this direction? Well, remember, it's plus to minus V2, so since we're doing the current leaving the node, we're getting the passive sign convention sets up naturally. So we have the current going down is going to be V2, and then that's flowing through a 1 ohm resistor. And then we're looking for the current going off to the left. And again, we're back to a voltage source. And what's the current through a voltage source? We don't know. We don't know the current through the voltage source. There is no relationship between the voltage source's voltage and its current. The current that flows through this voltage source will be whatever makes the rest of the circuit happy. That is, satisfies KCL, KVL, Ohm's law. And so what we have here is this red current going to the left is obviously the opposite, going in the opposite direction from the I question mark we found earlier. So this will be a minus I question mark equals 0. So the nodal analysis tells us that we're going to get, in this case, 2 equations and 2 unknowns. But then we see we have a third unknown that is cropped up. And where did that third unknown come from? Well, it's the fact that we have an I question mark. So So I question mark, we got to look at this I question mark. Why does it come about? Well, it comes about because of this voltage source. So the voltage source causes us not to know the current, therefore the voltage source needs to help us out and figure out a relationship. So what do? We need one more equation that's derived in an independent manner so that we'll have 3 equations and 3 unknowns. And if you look at it, well, what does it mean to be a voltage source? A voltage source, in this particular case, the voltage on the left side is going to be 7 volts higher than the voltage on the right side. That's what the plus and minus in the voltage source means. I know that the left side's 7 volts higher in energy, 7 joules per coulomb higher in energy than the right side. Therefore, we know that V1 is going to be 7 volts higher than the other side, V2. And now we have 3 equations and 3 unknowns, and we can solve these. And when you do, use whatever method you want, back substitution, matrix inversion, Kramer's rule, and when you solve these, you'll find V1 is going to be 8 volts and V2 is going to be 1 volt. And once you have that, you can now find any voltage or current you want in the circuit and any power you may need. And so at this case, you've kind of busted it open. And so we see when we have voltage sources in our nodal analysis, we can't find the current. Remember, nodal analysis is applications, a systematic algorithm for KCL, and we can't find the current in a voltage source, so voltage sources give us a bit of trouble. Well, when we look at it, this is how you solve it, and that works, but let me show you kind of a shortcut method, if you will, and it's just kind of a different view. So here we have the same circuit, and we've kind of progressed our way through it. And remember, we have the unknown I question mark currents, going this direction, and going back to the left, we have basically negative I question mark. And so we have these 2 equations. So let's stop there before we continue. And let me show you kind of a different view of solving these nodal analysis problems that have voltage sources. Remember from algebra that when you have a system of equations, you are allowed to take 2 equations and add them together. All right, that is allowed. So let's do that. So we add these 2 equations. All right, this is the KCL equation from 1, and this is the KCL equation for number 2. Let's take those 2 KCL equations and add them together. And when you do that, you'll get minus 3 minus 2 plus V1 over 2 plus V2 plus I question mark minus I question mark equals 0. So because we're allowed to take two equations in a system and add them together, this is the equation that will result. And then, of course, it should jump out to you immediately that those 2 terms will cancel. Remember, I question mark was a value that we didn't know what it was, so we had to create a variable for it. And when we take those 2 equations and add them together, those 2 terms will cancel. And that's because what we're doing is basically we're adding together those 2 current. They're going it's the same current. They're in opposite directions, so they have opposite signs. And so now we have the equation minus 5 plus V1 over 2 plus V2 equals 0. So we have 1 equation and 2 unknowns, and so we need to get 1 more equation. And so that comes from simply what we saw earlier, is that we know that the V1 side of the voltage source is going to be 7 volts higher than the V2 side. And now we have 2 equations and 2 unknowns, and when you solve these, you'll get the solution, as before, that V1 equals 8 volts and V2 equals 1 volt. Well, what we have is the idea of supernodes, and this is how we apply it in practice. So let's kind of pretend that we're starting this problem from the very beginning. All right, so we've labeled our voltages V1 and V2 with respect to our reference, and so let's get started. Let's write KCL for node 1. All right, so what's the current going down in this direction? It's going to be minus 3. What's the current going down in this direction? It's going to be V1 over 2. What's the current in? Oh, we can't do that. There's a voltage source. So what we do is we create a supernode. All right? And so what you do in a supernode is you basically take the voltage source that's going to give you problems, all right? And we're going to make a node which is really both nodes, the nodes on both sides of the voltage source in question. All right, and so now what we're doing is, instead of writing KCL for node 1, we're writing KCL for the supernode, and the supernode is contained there in the dashed line. So the supernode currents are going to be down in this direction, minus 3. All right, V1 over 2. Now we need the current going in this direction, and that's going to be V2 over 1, and then the current down in this direction, and that's going to be minus 2, and that's all of the currents leaving the supernode, and that equals 0. So now we have one equation and two unknowns, and if you look, that is the exact same equation that we found right here by adding those two equations together. So the supernode, by combining the two nodes, node 1 and node 2, writing KCL for the currents leaving the supernode, what that does is that gives you the equation that results when you add these two individual equations together. Now, of course, we still have one equation and two unknowns. We need one more equation, and that again comes from the fact that we know that V1 is going to be 7 more than V2. And then we can solve and find the answers of 8 and 1 once again. All right, let's go to another example. Here we have a circuit, and we see that we have a voltage source in it. And so since we have a voltage source, we're going to expect to find have a supernode. So let's begin. How many nodes are in the circuit? Well, look at this real quick, and you should see that n equals 3. All right, so I'm going to have two equations I'm going to be writing. And so let's define it. We'll call this V1. We'll call this voltage over here V2, and let's get started. Well, to get started, we're going to start writing KCL for node 1, and we immediately realize that node 1 has a voltage source connected to it. So we should make a supernode. But in this case, if we try to do a supernode, the supernode is going to be all the stuff in this direction, but we see that it's actually our voltage source is tied back to the reference. And so, you know, how do we deal with that? Well, it's actually, these circuits, when you have a voltage source connected to the reference, it's actually much, much simpler than you think, because what we see is if we can immediately write down the fact that what does it mean to be a voltage source? Well, I know that this side of the voltage source is going to be 33 volts, 33 joules per coulomb higher than the bottom. So I see that immediately V1 equals 33, and the equations can't get much simpler than that. So when you have a voltage source connected in your nodal analysis to the reference node, it basically gives you the answer straight away. V1 equals 33. The voltage at this point has to be 33 volts higher than the reference, therefore V1 is 33, which is exactly what we are after. So then we got to write the KCL equation for the second node, and we have V2, and that's going off to V1, but we know that's 33, right? And that's going over through a 3 ohm resistor. And then the current going down, well, let's go in the opposite direction, so it's 2Ix. And then I'm looking for the current going down in this direction, and that's going to be V2 over 2. And that's all the currents leaving node 2, so that equals 0. So here's our second equation, our two equations, and then we see we have 3 unknowns. And why do we have a third unknown? Well, the third unknown is this Ix. It comes from this current source. So this current source needs to help us out. So we're going to look for the definition of Ix, which is given to there. And then we can write our next equation, and that is, what is Ix? Well, Ix is simply the current. And it's the current flowing to the left, which is going to be the negative of this current, which we've already found. All right, and so we know Ix is going to be minus V2 over 2. And then when you solve this, and again, Cramer's rule, back substitution, matrix inversion, whatever turns you on, V1 is going to be 33 volts. Obviously, we saw that right away. And then when you solve the other equations, you'll find that V2 equals 6 volts. And then once you have these two numbers, you can find any voltage in the circuit you want and any currents and then any powers. All right, let's look at a complicated example, more complex example. And so this is very similar to the circuit we saw earlier, except now we have a voltage source, so it's going to give rise to a supernode. And so we need to figure out how many nodes we have, and you can get your little colored pencils out and you can start coloring here, and then you can come along and you can color these guys, and then you come along and color these guys, and then the one at the bottom, and the bottom probably is a good spot to be a reference node, and so we'll do that. And then once you have this and color all the nodes, you can then redraw it, and you'll have an equation that looks like this. So here we've got the colored nodes, and I've already defined my node voltages V1, V2, V3, all with respect to my reference down here. So now, we're ready to hop in. So, I have 3 node voltages, I expect 3 equations. So let's start writing KCL for node 1. KCL for node 1. So what is the current going off in this direction? Well, the direction of the arrow is opposite, so it's a minus 8. The current heading off in this direction is going to be V1 going to V2, and that's going through a 1/3 ohm resistor. And the current going around this way, well, that's opposing the arrow, so it's going to be a minus 3. And then we are going for the current around here, and that current is a voltage V1 going to V3, and that's passing through a 1/4 ohm resistor, equals 0. And if you go back to the previous lecture on nodal analysis, you'll see this equation matches that equation exactly, because the connection of elements to the node 1 has not changed, so we get the exact same equation. So now let's come along and do KCL for node 2. And before you get started, you can we'll just dive in. And so we have the current going in this direction, and that's going to be V2 heading off to V1 through a 1/3 ohm, and then the current going off toward the reference, well, that's going to be simply V2 over 1. And the current going around this way, it's the same direction, so it becomes minus 3. And then I want the current going this way, and I see, oh, it's a voltage source. What's the current through a voltage source? We don't know. So we need to form a supernode, and so we'll make a supernode. The 2-3 node becomes combined into a supernode, and so really what I need to write is the KCL for the supernode. And so, picking up where I left off, I've already got this current and this current, so now I need this current, and that's going to be V3 heading off to V1, going through a 1/4 ohm resistor. Current going off in this direction, they agree in sign, so it's simply going to be minus 25. And then the current heading off in this way is going to be V3, and that's passing through a 1/5 ohm resistor, and that's all of the currents leaving the supernode. KCL says that equals 0. So here we have 2 equations in 3 unknowns. So we need one more equation. And why do we have only 2 equations? Why did we lose an equation? Well, it's because of this voltage source. And so since the voltage source caused us to lose an equation, we need to require the voltage source to give us a new equation to go in its place. And we need an independent equation, and we have one, because what does it mean to be this voltage source 22 volts? Well, to be a 22 volt voltage, what it means is we know that the V3 side is going to be 22 higher than the V2 side, because we know the voltage is plus to minus. We know that the right-hand side is 22 volts higher, 22 joules per coulomb higher than the left side. So we get V3 equals V2 plus 22. Now we have 3 equations and 3 unknowns. And then you can solve. And if you solve this, again, Cramer's rule, back substitution, matrix inversion, you'll find V1 is minus 4.5 volts. V2 will be negative 15.5 volts. And V3 will be 6.5 volts. And you can go check those and make sure that you're doing your number crunching correctly. So here we've seen when we have nodal analysis, and we need to have, and our nodal analysis involves voltage sources. So if you have a voltage source in your nodal analysis, then that means you're going to have a supernode. And the reason that comes up is because a voltage source, we don't know the current flowing through a voltage source. And remember, nodal analysis is an application of KCL. If we don't know the currents which are flowing through a voltage source, then we have to do something else. So we combine 2 nodes, make a supernode, and then the voltage source itself gives rise to the equation to make up for the fact that we've lost one. Okay, that's nodal analysis with voltage sources and the idea of supernodes, which is basically an idea to help you kind of simplify a few steps in your algebra. Go practice lots of these. The best way to learn nodal analysis is just work tons and tons of problems and enjoy, and come back and we'll look at our next method next time.